Hi, good afternoon. Oh. My name is Alon, this is Igor. Today we're going to talk about using graph partitioning in the design of distributed systems. We're going to start by talking about the challenges of combining social networks and distributed systems. Then we're going to describe the graph partitioning algorithm and how it can be implemented efficiently in a distributed manner. And last, we're going to show how one can use graph partitioning to improve the efficiency of systems in production. So let's start with distributed systems. We all know why we need them. Sometimes a single unit of computation simply can't handle all of the load. We have some unit that has CPU, RAM, or disk, or bandwidth, and that unit can't take all of the incoming queries or can't store all of the data. And the typical design choice here is to scale horizontally. We take that unit and replicate it many times in order to increase the amount of the resource we're lacking. However, now we are facing the question of how to distribute queries or data, or both, across these new units. So there are many ways of doing that, many choices here, and one of the most important attributes in any of these choices is the fact that the split or the partition now should be balanced. We want to make sure that any one of these units receive the same amount of queries or store the same amount of data in order to make sure that none of these units is overloaded and that we are not underutilizing the rack. And so we want the partition to be balanced, and randomness many times is a very good choice here. We decide just to route randomly or to shard randomly, and almost automatically we receive the desired balance. However, randomness is a suboptimal choice for social networks. In social networks, many times, most of the times, your queries are actually not about yourself. They are about others, the people you are socially connected to. People ask questions like, what's new in the life of my friend whenever they want to build, whenever we want to build someone's newsfeed. People ask questions like, who's currently online when we want to build the chat presence unit for chat. And people ask questions like, who's friends of X when we build X profile page. So these questions are about data that was produced by other actors in the system, not by the viewer of the current page. And these queries, it's quite easy to see, these queries retrieve multiple records at the same time. So it's not just one record, it's many records about all of my friends or all of my social connections. And most importantly, a lot of these queries overlap. So if I query some set of records and as someone who's really close to me, maybe a good friend of mine or part of my close social cycle is issuing the same query, there is a very high likelihood this guy is gonna fetch a very similar set of records simply because we have many friends in common. And we can say that query pattern is local in the sense that users rarely query the whole graph, but most often they query a local subset of the graph that represents their closed social environment. So why it matters and how come random is not a good choice here? Let's see a concrete example. We were experimenting with a system at Facebook that was CPU intensive. It had 200 hosts calculating some information on behalf of the user on top of large data coming from his friends. Whenever a user was performing a query, his query was routed randomly to one of these hosts in order to keep the load balance. That host was then fetching data from an external database about the friend of that user in order to perform the final calculation. Now, it turns out that after removing the CPU barrier here in terms of the efficiency of the computation, the next bottleneck was actually bandwidth. Fetching data from these external databases was an expensive operation. Bandwidth was low, a lot of data needed to be flowing through these communication lines. Database operations were expensive, and the designers of the system looked for ways to reduce incoming bytes to any of these hosts. So they made two choices. The first was to cache all of these records locally on the RAM of the machines in order to reuse them in subsequent queries. And second, in order to make that choice even more effective, they decided to keep the routing scheme as a random scheme, but make it consistent, meaning that if the user will get back to the system, he'll be routed to the same host and he'll reuse its own cached elements. However, this is a social network. Whenever another user is approaching the system, the fact that routing is random means that most likely he's going to be routed to a different host. Whenever Igor is going to reach the system, he's going to be routed to another box in the rack. He'll probably find an empty cache, even though he could be sharing a lot of shared records with me. So we see that there is a lost optimization opportunity here. What we really want to do is to route users, socially similar users, to the same host, but at the same time keep the balance. So the question is, can we do so? Can we make the queries more socially aware, but at the same time keep the overall balance of the system? So one way to think about this problem is to think about it as a graph problem. In this graph, vertices are users that generate queries to the system, and edges between them represent friendship ties between them. And the question we ask is, how can we bucket the vertices of this graph and assign each one of these buckets to a host, or think about the users in this bucket as users that generate queries, and assign these queries to any of the hosts in the system. Let's, for example, think on a simplified version when we have only 3 hosts. We want to think, how can this bucket be partitioned into 3 buckets? And we want to assign each one of these buckets to each one of the hosts of the system. Now, we care about 2 important qualities. First, we want to make sure that none of the hosts receive too much work to do. So we want to make sure that each one of these buckets has exactly the same number of users or vertices. You can see here that each one of these buckets has 6 vertices. And second, and this is the reason that we decided to model this problem as a graph, we want to make sure that each one of these buckets is social, or let's be more specific, we want it to be dense. We want to make sure that if a user, if any of you is assigned to any of these buckets, so are most of his friends. More practically, we want to make sure that most of the edges of the graph are contained within bucket and not split between buckets. As you can see here, this is potentially a good bucketing of the graph because only 6 edges cross between buckets. So this is a known problem. Many people worked on that problem in computer science for many years, and it's basically an NP hard problem, meaning that it's not easy to find the optimal solution, but there are very good approximations to this problem. The main problem is that most of these approximations are not scalable. They assume that you work on a single machine. They assume you have only 1 thread of computation, that there is a shared state in memory that all threads can look at, or many such limitations that make it a hard thing for data set at the size of Facebook. So in the next few slides, we're going to show how graph partitioning can be calculated efficiently in a distributed manner in order to support graphs at a scale at Facebook.
So now you know why are we going to need a very good graph partitioning, but the question is how are we going to calculate it. So we can start with a simple case with just having 2 buckets and trying to see how can we get a good graph partitioning. We can start naively by assigning vertices to these 2 buckets in a balanced manner and completely ignoring how many edges are crossing between those 2 buckets. So now we have a perfectly balanced state, and we can now try to improve this state by moving vertices and while keeping the balance throughout. So how can we do that? We can find a particular vertex that has more neighbors in the other bucket. If we move that vertex, we have reduced the number of edges that are being cut. But we have affected the balance, so we cannot just move vertices as they want. We need to find another vertex that has more neighbors in the opposite direction and move it back. So basically what we are doing here, if we are swapping vertices, we are keeping the balance throughout, but we are improving the partitioning. And we can swap vertices as long as there are any swaps. In a more general case, if we have n buckets, we can do something very similar. We can look at any particular vertex, look at where all of their neighbors are, see where it has the most neighbors to, and say that that vertex wants to move that particular bucket. Now we have calculated for all vertices where they want to move. We can look at any pair of buckets and apply as many swaps as we want. So we can apply swaps as we want until one direction runs out. So if you apply this on the whole graph, we're going to have a lot of swapping going on, and then at the end, there will be still a lot of vertices that want to move, but nobody will want to be moving with them. So what we can do, instead of looking at just the best particular, on the bucket that has the most neighbors, we can look at all other buckets that have more neighbors than our current partition. So we can look at the vertex that nobody wants to swap with, and look at some other bucket that has also more neighbors than its current bucket, and say that that vertex now changes mind and want to move to another bucket. And this will allow more movement to happen. So actually in social graphs, this works pretty well. So probably because social graphs are like pretty sparse and have a lot of structure. But the problem is scale. In our case, we are working with graphs that have billions of vertices and trillions of edges. We cannot fit everything on a single box. We cannot run everything on a single CPU. So what we need to do, we need to create a distributed algorithm that will scale both the data and the computation. So we are going to use a Giraffe framework. This is a graph processing framework the previous speaker talked about. Just to remind ourselves, it basically distributes the graph across the machines. Basically takes the vertices and assigns them to different machines. It has one particular machine that is a master that is coordinating the whole process. It allows local computation, so each vertex can do a computation based on data it has locally. And it supports message passing. We can send messages between vertices, and we can send messages between vertices and master. So we're going to take our initial naive approach and try to implement it on top of this distributive platform, and we are going to create the iterative algorithm that we are going to repeat this next set of steps until the algorithm converges. So first, we are going to take all vertices, and they're going to make their own individual decision. In order for this to be efficient, they have to know, they have to have all the information local to make such decision. So what do they need to make the decision local? They need to have information about all other buckets, how many neighbors there are in all of the other buckets. So if they have that information, they can easily see how many neighbors there are in the current bucket, how many neighbors there are in the best bucket, and see which bucket they want to move. After each vertex has decided when it wants to move, it will basically send that proposal to master. Again, we will not be able to store every single proposal on master because it's on the order of number of vertices. So what we're going to do, we're going to aggregate it in a matrix that will represent how many vertices want to move between pairs of buckets. So now we're going to decide who is going to be allowed to move. Again, if you remember previously, we cannot move anybody as they want. We can only apply swaps to keep the balance throughout. So what we're going to do, we're going to take this matrix and calculate who can swap and who cannot. And we're going to do that in a centralized manner. So what we're going to do, we're going to take a pair of buckets, look at how many vertices want to move in each direction. So for example, here we have 3 vertices wanting to move from bucket 1 to bucket 0, and 5 vertices wanting to move from 0 to 1. And we're going to take the smaller of those numbers. We're going to say that all of those are going to move, and we're going to calculate the fraction of the others that are going to move. And now we're going to calculate that for the whole matrix. And now that we have calculated this, we need to announce to vertices whether they should be moving or not. Again, we don't have information for every particular vertex whether they're going to be moving or not, so we're going to send this matrix back, and you're going to use these fractions as probabilities whether you're going to be allowed to move or not based on your decision in the previous step. So now each vertex flips a coin with that probability and decides whether it's going to move. We're going to update our local state, but we also need to send to all of our neighbors that decision so that they can update their local state that we used in the first step. So we have implemented this on top of Giraffe. We're using it for various different graphs and various different scales of number of buckets. So for example, for this particular example of the system, we used all users, which we have 1.3 billion vertices. We split them into 200 buckets. And we got around 3/4 of edges being within a bucket, and only 1/4 of edges being crossing. We are running this algorithm on top of Giraffe cluster, which has 100 machines to split this huge graph into. And it takes around 6 hours, and it needs only 30 to 50 iterations to converge to a very good state. So now we're going to get back to the previous system. We used this graph partitioning technique to take the whole active user space of Facebook and bucket it into 200 buckets. So any of you who now has a Facebook account is assigned to one of these buckets, and so are 85% of his friends on average. We then took these buckets and assigned each one of these to any one of the hosts. So we had 200 buckets and 200 hosts. And during query time, we first looked up the bucket that is associated with the user and routed that user to the corresponding host. As a result, cache hit of the system increased. More importantly, cache miss rate was halved. And as a result, the bandwidth was decreased by 50%. Remember, that was the bottleneck of the system, meaning that a different routing doubled the capacity. So we are at the summary. We demonstrated that it's possible to produce high-quality partitioning of large-scale graph in a scalable manner. You don't need a huge machine in order to do that. You can implement the algorithm we just demonstrated on top of your own hardware at home.
It's an optimization opportunity for many graph-based data set. We showed an example for social data, but it actually should work on any large-scale sparse graph, like the web graph, network graph, biological graphs. And we've demonstrated one application in routing, but the exact same ideas, it's quite easy to see how they fit sharding or batch or any big batch processing infrastructure in order to improve their efficiency. So that's it. Thank you. Thank you. We can now take your questions if you have any. Yes, please.
So you do this like at Facebook, right? I was thinking.
Let's just wait for the microphone.
No, that's good.
Sorry. Yeah.
So yeah, I was curious if this structure is used in the content delivery networks also. Like, I was trying to visualize how do you replicate all this.
What do you mean? Can you repeat that?
So like when you say load facebook.com or load my page, right? It needs to get that page from somewhere, right? So you say you look up this person. So I was kind of trying to relate if you do this partitioning like on all the hosts that are used in the content delivery networks. So
Yeah, so we can't give too much information. We use it all over the place in many different applications, but I can't give specific. Sorry about it.
Can you make the can you actually relax the constraint that each rack has the same number of users and make the algorithm a little more?
So in a sense, when we are talking about balance, what matters is the most loaded machine, right? Where your capacity is dictated by the most loaded machine. So if you have imbalance of 5%, that directly decreases your capacity by 5%. So in a sense, you basically can trade balance by improvement in quality that are more than what you basically if the gains are more than what you lose from the balance. And in most cases, almost perfect balance is almost optimal. So if you're trading more, if you relax balance versus what you're gaining by the quality of improvement in the system.
I think one more element here is the fact that we've demonstrated numbers were always numbers of users or number of edges, but it's easy to relax these to be weights. You can think about giving weights to different users and making sure that the buckets are weighted, and giving weights to edges and making sure that the sum of weights is minimized, not just the number of weights. So you can play with these ideas to maybe to achieve different types of balance. Yes, please.
I actually have two questions. So first question is, so social networks evolve, so how often do you have to find yourself to recompute the assignments? And the second question is, so I feel like in distributed computing, you mostly find system hashing to assign objects to buckets, and your hashing is actually stateful. So how much kind of overhead do you encounter due to it being stateful and not being consistently being able to recompute the assignment?
Yeah, so for the second question, so for the first question, when you need to update, we are updating like every week, and very few vertices move, and in a sense, there is still a lot of friendships that are being added, but that doesn't affect much. Like your initial friendships mostly affect where you are going to be. And only basically new users are mostly the users that are being moved. And I forgot.
Consistent hashing versus stateful.
Oh, so in this case, you can store the mapping from user to a particular bucket is small enough that you can store it in RAM on one or a few machines. So the overhead is just like a RAM lookup. So in a sense, it's pretty cheap to do so.
Yes.
If you 1.5 minutes.
So you provide a clever and simple algorithm for doing this clustering. And it gets the 50% reduction, and you mentioned it's used in other places that you can't mention, and get some other reduction that you can't mention. That's okay. With a lot of these algorithms, often doing the simple thing gets you most of the benefit. And then if you spent a long time and did some PhD level research and got the optimal thing, it would only save you a little bit more. Do you have a sense for how much more algorithm improvements could help? I mean, is the 50% reduction, once you have the 50% reduction, the things you're bringing in, are they things that you wouldn't bring in, kind of required things to bring in because somebody who doesn't update their Facebook page very often is always going to be out of cache? Or is there room there to reduce the 50% to 10% or even better?
So I would say that we've demonstrated some of the features of this algorithm. We later on introduced many others, and the most of the gain came by just implementing it. So there was a lot of low-hanging fruit just because the graph has lots of structure. You need to do a very simple thing to uncover this structure, and you automatically gain something. You can move the needle even more with smarter ideas, with more work, but it's not in the same order of magnitude. I mean, it's harder to reduce the bandwidth by another 50% like that. We've got no more time for questions, so we'll be really happy to answer your questions later on. Thank you.